Hey everyone, welcome back to another full-length YouTube tutorial. We're going to be going over generating fractals using VEX. This serves as an introductory to VEX as well if you're not super experienced with it. I'm going to go over all of the basics, fundamentals very quickly at the start of this. So just generating these shapes or these patterns using a few lines of code. We can get into variables, attributes, functions, some very basic mathematical operations. We get to generate all kinds of interesting patterns and structures and forms using that very simple routine that we're going to explain later on. We can even get into 3D fractal generation. If we look at these different 3D shapes, you can generate them using the same method. And the whole process is explained in depth. It's a very simple routine, just looking at the different vertices or corners of a shape, moving a set or determined distance towards those vertices, and then drawing a point. And over time, when you do this, you repeat it enough, you get these really cool self-similar repeating structures called fractals. Get into all kinds of interesting business going forward. Okay, I'm going to jump in and go over some kind of VEX Wrangle basics. So just make a geometry container at the object level, double click to go inside, and then I'm going to make a single point using the add SOP. So I can click this box here to enable it. And when I do that, you can see we get a single point placed at the origin. You can move it around doing these coordinates with the middle mouse button and then moving the mouse left or right to change the values. You can also type in specific coordinates if you want to shift the point around. You can also go over here to the transform handle and move it around visually that way. And then we're going to use a Wrangle node. So this will run VEX code over points. And whatever code you type in here, it will run over every single point simultaneously. So if I connect it like this, we'll just do a very simple operation here, which will be at p equals 0. You can do hold down control and enter to commit or to compile the code. And you can see when I did that, the point snapped to the origin. So what we're basically doing here is overwriting every single component of these coordinates to 0. And the way that this code works, whatever's on the right side of this equal sign gets set to the left side of the equal sign. So in this case, we have the P attribute, and we're setting it to 0. You could do more complicated arithmetic or stuff like that. So we'll evaluate here 4 plus 0, and that would set the point to 4, 4, 4, 4, each of these values. And when you start to do a little bit more advanced operations, you might want to check or like debug the actual attribute values instead of relying visually, like in 3D space. Sometimes things can be deceiving. So I'm just going to go up here to the pane tab operations, go down split pane top bottom, and then go to this plus new pane tab type inspectors geometry spreadsheet. And I'll close that first tab that it came with. And now we can work and we just have a little bit more information that we can see as we're working. And one more thing I forgot to mention is this semicolon is used to just indicate that that's the end of the line of code. So it just tells the computer that's where this line of code terminates. And what I was saying earlier with it running over all of the points of the geometry simultaneously, if we just put down the quick pig head and plug it in, you can see that every single point of the pig head has been updated or set to 0. So that's what I mean. We go from here and every point shifts or gets overwritten to 0. There's nothing fancy or extra you need to do to tell it which point you're running over. So it takes a little bit of time to get used to how this works, but this is running over whatever you type in here will run over every single point in parallel, multi-threaded, super optimized and stuff like that. So it has its advantages and disadvantages. If you want to do specific things, it does have like detail mode, and then you could run specific lines of code over points or do some more advanced operations like that. Okay. So here we're just overwriting an attribute with a value. If we want to work instead of attributes, we have something called variables. So you have to declare these variables and tell it what data type you want it to be. Vector is usually a coordinate or a color or something like that. There's also floats, or just a single floating point value, like a fractional value. And then there's also integers that are like whole numbers, and then there's some more advanced higher dimensional data types as well. We'll just start with a vector, then you tell it its name. I'll just call this offset. And then you can use the equal sign, so we'll tell what this variable should hold. So I'm going to use these curly brackets, like the Egyptian brackets, and do 0.5, 0, and 0. So we can do p equals offset. And we see that the point moved now. So this is a little bit of a difference. This is an actual attribute that stays on the geometry, even as you add new nodes and everything like that. This is a variable. So it's only stored while this code is running. It doesn't exist outside of this node. So it's just when you're naming things, or why you see people using one over the other. That's the reason. You don't usually want to add a lot of extra attributes to your geometry each time you run these. So if you need like a temporary thing to hold data, this is where variables come in. You can do more advanced things with it. Instead of just overwriting the existing values, we can do p plus offset. So instead of overwriting, this is just modifying or adding to the existing coordinate or data. So we're just shifting over by 0.5 units. So it's quite literally an offset in space now. And if you've ever used the transform node, this is pretty much the same operation that we just did. Shift x over by 0.5 units. And we're in the same exact position now, either way. So that's pretty cool. If you want to be a little bit more minimal, I'm just going to comment this code so it will be disabled. And you just do that with 2 forward slashes. You'll see it turn yellow to indicate the computer's ignoring it, but the compiler doesn't consider it. And I can do p plus equals offset. So this is doing the exact same thing. This is just a more compact way. Instead of having to use this attribute twice, you can just leave it on the left side of the assignment. And instead of setting or overwriting itself, now it's adding to itself. So it's a little bit more advanced. You can also do, if you really want to be super minimal, they have just p++, do a semicolon. And what this does now is we're incrementing each component by 1. If we wanted to address a specific dimension or a specific axis or component, you can do p.x. So in this case, now we're shifting over by 1 unit. So that's pretty cool. It's only useful for specific if you want to increment by a whole number, but if you need to like count or keep track of something, it comes into play then. So another thing we can do besides just these simple operations, they have something called functions. So I'm going to use this add point function. And as soon as you do open parenthesis, it does a good job of bringing up this little tooltip or help. So a function, instead of like assigning or changing a value or something, this does a specific operation behind the scenes, kind of like it runs a little program you could think of, and then returns or does a result or does an operation for you. So in this case, this is going to add a point to the geometry. And you look at this one here, add point. Inside of these parentheses is going to be the arguments that it expects. So you have a function and then you have arguments. These are kind of like parameters or settings that you need to tell it. 0 just says add a point to myself or the current node. And the next one is just what position you want to add the point at. So I'm going to use these Egyptian curly brackets again, and we'll just set these all to 0. So when I did that, you can see we added a point, created a new point at the origin or at 0, and it also shows up in the geometry spreadsheet down here. So we've now kind of replicated this node operation, just adding a single point with coordinates. And we've just done it with a single line of code here. It's pretty minimal or pretty compact. So as you start to do more complex operations, you can even replace sets of 8 or 12 nodes or something like that, and kind of organize or structure your network here to be a lot more optimized or clean. And we could keep going, and I'm going to change this right now to just be P. So we're going to add a point where the current point is. And if we turn on point numbers, you can see they're overlapping. There's like a 0 and a 1 on top of each other. I press the D key over the viewport. We go into guides. I'm going to change the guide font to large. So that just makes these point numbers a little bit easier to read. So we added a point where our current P or position attribute is, and we could do another operation afterwards that will be P plus equals offset. So what we did was add our new point and then shifted our point over after we added it. So just order of operations, if we did do this earlier, we would have moved our point and then added it where it exists. So you could see the order that you put in these lines of code is super important. Everything just goes top down. I'm going to adjust this offset to be a smaller distance or smaller increment, and we can copy and paste these lines of code to repeat them. So I'm just using Control C and Control V, and we can quite literally just keep repeating these steps over and over to draw a little path or draw a little line. But that's obviously a little bit redundant or probably sloppy. It takes up a lot of space in this code editor, so it's just in general not a good idea. If you're going to be doing an operation a couple of times, like more than 2 or 3, it's usually a good idea to start using loops at that point. So loops is a special kind of flow control thing that you can use. We'll use a for loop here. We're going to do for a specific increment, an incremented amount of times, it will just keep repeating these operations inside of the loop. So the first thing you tell it is what to count, what's going to be your increment. I'm going to make an integer that's called I. So the I just stands for increment in this case. And we'll set its initial value or initialize it to 0. So we're going to start counting at 0. And then the next one, you want to tell it while this condition is true to keep doing its thing or keep looping. So while I is less than 5, it will keep repeating. And then the next or the last thing you need to tell it is what to increment. And pretty often, or almost all these, you just do I or whatever your counter is plus plus. So each time this runs, it will add a single value or a single number. We'll just increment I by 1 until it exceeds 5. And then we just need to add these curly brackets. I just tabbed over. And this will indicate the loop start and close, or the open and close of the loop. And it already updated, and we have already repeated our operation now 5 times. And usually when people clean this up, they'll tab these lines in. So this just makes it easier to read when you scan down. Instead of everything being left justified, you can easily tell what's included in the loop. So we have a lot of pretty cool control now. If we want to do larger repetitions, we can do this. You can even start to do like crazy high numbers. And you can see everything's still running pretty quickly. So we can add tons of points kind of in rapid succession without much of an issue, this method. It's super cool. So everything we've done so far is kind of simple operations, just setting values, getting values, incrementing, offsetting, or things like that. I'm going to bring a new function into play, and that's going to be the random function. So if we just look at this tooltip here, this will generate or create a random number between 0 and 1 from a seed. And this is another function. This is actually going to return a random number. If you want to just like debug it, sometimes I'll add an attribute to the geometry. So if we'll just say my random and set it equal to this rand, and for the seed, I'm just going to type in a number here, and we'll close it. So it only gets added to the current geometry that you ran this with. For attributes, it doesn't get considered for these points that we've added later on. But we can see it's generating a random number. And if I change this value here, this is what's called a seed. So each time I update this or adjust it, we get a different random number. It's kind of like rolling a new dice, or like spinning another wheel and like letting it select a random number. For computer programming, people almost always use seeds for their random numbers. So you can, if I send this code to someone else, they're using the same seeds and they can reproduce the same result. If you just let it completely choose a random number without fixing it to be like keyed in from a value, then you would have a much harder time like replicating it. Every time you opened your file, you might get a different result, and it would be kind of crazy. So that's why you need to seed your random number generators. So just get rid of that. And I'm actually going to use it up here, and I'm going to set the P, the position, Y component equal to a random number. So you can do that. So you can see what this did is it updated every single height or elevation from that random generator, but it's not changing per point because we're using this constant seed. So if we replace that with I that we're using to index or increment our loop, when I do that, now you can see each point gets shifted by a random elevation, or it gets set to a random elevation. And then we add it, or we record its position, and then we just keep doing that over and over again. So that's pretty cool. We can add some natural, kind of unexpected or chaotic elements to your code this way. And right now, everything's just between 0 and 1. So if we look at py in our spreadsheet, all of these values here will be between 0 and 1. If you want to remap it or change the range, there's some fancy stuff you can do to accomplish that as well. So we can take this and multiply it by 4. And now we've just stretched or scaled up our random range. So we're going between 0 and 4. You can also click on these to sort numerically. So you can see our highest number is 3.99 something. Lowest number is very close to 0. And if you want to have a little bit more kind of like control over this, sometimes what people will do is they'll use this floor function. And I'm just going to close it. So this is just a mathematical operation that discards the remainder, the fractional remainder. So it just leaves you with the whole number. So the whole number is like the integer before the decimal. We're discarding the fractional result using this floor. So this is a pretty useful method if you want to select something. Like I either want 0, 1, 2, or 3. Then you can use this and you'll know that you'll be getting like a specific number. Even this way you can set something between 0 and 1. If you wanted to mix between two specific colors without any like blending or anything happening, this would let you do something like that. So you have a little bit of control. Can go up here, just random numbers between 0 and 41. It's pretty cool. You kind of have to remember that computers, they always start counting at 0. So because we're doing floor and then multiplying by 42, we're getting 42 unique random numbers, but they just start at 0 and end at 41. So that's a little bit of a gotcha. But other than that, that's pretty much all we need to know in terms of VEX coding to get started. If you're more curious, you can always click this question mark, search online. The Houdini help has a pretty good library of functions. I think if you just click here to VEX language, there's a pretty good like overview. It's a little technical. You can also find the complete library of VEX functions. So this is a really useful page to have open as you're learning VEX. So I could even search here. I could probably just do like Control F for search, and I could find floor. You'd see here this is literally the operation that I was doing over here. It just returns the largest integer less than or equal to the argument. It's a little bit alternative way to say it. I like to think of it as just discarding the decimals and just leaving you with the whole number. But yeah, it's rounding down to the nearest whole number is another way to think of it. So yeah, you can do that. You can see related functions. So this is super useful kind of glossary to have with you as you're getting started typing VEX code, or you see a function, someone's using a function you haven't heard of or seen before. It's super useful. We get on to some of the more fun or interesting stuff now that we have the basics down. So what I've done is prepared an animation of what we'll be doing as like a visualization. And I've also typed up something called pseudocode. The pseudocode is just a brief summary of what you want your program or your task or tool to accomplish. So you just break it down to the kind of easiest or smallest steps, and you just type it out in like plain English or whatever your language is, not like a computer language, just whatever you're used to writing in. So the idea is just to get your thoughts out. You establish a plan, and you can start to break these down into the simplest operations, and then you can start to think about like translating that into the computer language, or VEX code in this case. So with this triangle here, we're basically just going to select one of the random points, the corner. We're going to move ourselves half the distance to that point, and then we're going to place another point where we are. And then we're just going to do it again and just keep doing it again and again and again. So over here, it's happening hundreds of thousands of times. And it's kind of the beauty of code, is that you could do these repetitive operations over and over again. It's super easy to do these kind of recursive or self-similar like operations. And self-similar is the quality of this. So it looks like the Triforce from Zelda, where it basically contains itself within itself. So as I keep zooming in, you can see this big shape just keeps getting repeated and repeated within. It's kind of mesmerizing or funny to look at. So just this is the simple code, and these are the visualizations of the operation. So just measure half the distance. We're going to select another random corner, move half the distance. And each time we're leaving a point, we're using that add point function. And we just keep repeating this over and over again. So we could get started now that we have our game plan out. What I might do is I'm just going to put this to always be on top. And we'll just have this up as a little bit of a reminder as we go. And we can get started. So I'm going to make a circle. It's a little bit counterintuitive, but if you're making an n-gon or a polygon of any shape, the circle is the easiest way to do it inside of Houdini. You can see we get like pentagon, hexagon, diamond, or rhombus or whatever, and here's our triangle. And then if we just rotate it, just going to flip it by 90 degrees in this case. We can even display the point numbers. If we do the D key, we might want these to be a little bit larger. This should match our visualization now. So we have point number 0, point number 1, point number 2. And then I'm going to do this blast node. And what I'm going to use this for, group type, I'm going to set it to points. The group, I'm just going to use it for point number 0, and then I'm just going to do delete non-selected. So if we look at this visualization, we're starting at point 0, we're just starting at the top, and we'll just do our operations from there. So here's our Wrangle, and we can plug it in. So the first thing we want to accomplish, or our first portion of the pseudocode, is selecting a random point of the triangle. So to do that, we're going to want to retrieve information from our triangle. So because it's up the chain, this Wrangle doesn't know anything about it. But we can reference it if we use these ancillary inputs. So this, you can wire it, and then this allows you to easily retrieve or access information from other inputs, other nodes in your scene. If you look at the bottom, you'd see it saying ancillary input, point saying you use 1, 2, or 3 to access, even though they're named input 4. So it's another thing with computers counting at 0. It's a little confusing at first, but hopefully you can get used to it. So if we want to select a random point of the triangle, we can use our random function. So this will be our, I'm going to make a variable that's going to be random point. We can use this random function. If we want to put a seed, you can just type some number in. This green squiggly line is saying your assigning a float to this integer. So it's a little bit, it's telling me to kind of be careful, or it's warning me about it. And you could fix that. What we were doing previously with this random, we were multiplying it by a number and then using the floor to discard the fractional amount. We could do the same thing here with a floor and can multiply it. In this case, we know we can multiply it by 3 because we have the triangle. And then when I do that, that error goes away. If I want to look and just check this attribute, or check this variable as an attribute, I'm going to do I at random point and set that equal to the variable, or assign that to the variable. So this happens to be selecting point number 2 that's going to be over there. I'm just going to regenerate this random seed until I get 1. So I'm just cheating a little bit here. I just want to match what's going on with our diagram. So I'm just kind of re-rolling this dice, or just selecting another random number until we happen to get 0.1. So this is like a hack. It's like a way to just debug your code if you quickly assign it to a attribute like this. But I'll usually comment it out when I'm not using it. This is usually a bad idea if you get in the habit of doing that and you leave too many extra attributes clogging things up. It'll kind of be cumbersome or confusing for other people to look at your scene. So we've gotten our random point. One thing that we can do that's a little bit of a nice thing to modify is if we change this from being hard-coded as 3, we can use a special function that's this endpoints function. And this is a really useful way to just check how many number of points are connected into this input. So if I do endpoints 1, this is a shortcut. If I look in middle mouse button here, you see this has 3 points. So this will automatically update or remap itself to however many points, and we don't have to worry about hard coding it to 3, which is a little bit cleaner to type it this way. And you can see our random point, it's still evaluating to the same number. So we've selected a random point of the triangle. That step, the first step is done. The next thing we want to do is move half the distance to that point. If we look at our visualization here, you can see what we want to do. So we find that whole distance and then cut it in half, and then move the point there, and then we're going to leave a point behind. This is getting ahead of myself. Okay. So we need to know the position that we want to move towards. We can do that making another variable, and this will be our target. And we can use the point function. This reads any point attribute from a geometry. So in this case, the geometry, the first argument is just going to be 1 for this ancillary input. The next argument is going to be p. This is a string, so you put it in the ticks like this so it turns green. You can do single or double quotes. Either one will be fine. This is just the name of the attribute. So in this case, we have p that we want to retrieve. And the last one is the point number. So we've already decided that, and we can reuse this variable. This would be random point. So we did it. Not all the way, but we've gotten our destination where we want to end up. If we just want to check our work quickly or see if it's correct, we can assign the position here to the target. You can see, sure enough, it moved along. This is a good skill or habit to get into, is like checking your code as you go along. If you try to type everything out and then just expect it to work, you won't know where it went wrong if it does not work the way you expected. So if you're doing it this way and like checking as you go, then it's a lot easier. You'll have a better sense of what's going on. So instead of just setting it, overwriting it to the position, we want to actually move towards that. And we can make a direction, and that's going to be equal to the target minus the current position. And again, if we want to proofread this or double check, I can assign, in this case, I'm going to assign the normal attribute, because this is a direction, or it's like a vector. And if we turn on normals, we can see that this is getting drawn. And if I do the D key over the viewport, if you look at scale normals here, this is just doing it by 20%. You can see now if we do it by half, that looks kind of what we want. Or if you want to visualize just the full amount without it being scaled, you can do that. So this is a common mathematical operation, kind of Pythagoras theorem type thing. You do the target minus the current position, and you get a direction or a thing that's pointing from your current position to the target. It's a little confusing. Took me a while to understand at first, but it's basically to minus from, and then you have a direction that's pointing where you're going to go. So we can get rid of that. And now if we do P plus equals direction, we moved, but we went all the way. So again, right now this is the same thing as just overwriting the current value, but we want to scale the direction or the amount that we do. So if I just add half or 0.5 times the direction, then we end up at the midpoint of the line. So that's why we need to calculate the direction vector like that. So we finished this step, we moved half the distance. If we look at our visualization, we did it. This is the full direction vector, and then we just scale it back by 0.05, and we offset our point to that, doing this plus equals, and now we just need to place a new point at this position to record where we are. So we can do add point 0 for ourself for the current geometry, and P for the current position. So you can see we now have the points overlapping like that. So we completed it. We just need to repeat the operations over and over again. We can use our for loop method that we were using earlier. And what I'm going to do is just go to the top here, start typing it for integer I for increment. We'll just initialize our counter or increment at 0. We can maybe just start with 100 iterations, or just limit ourselves to 100 iterations. And we're just going to use the standard increment of 1 unit or 1 value. And then we can use the tab over and put down the curly bracket, and at the very end close our curly bracket. So you can see it's not what we expected. The issue is we're not updating our random seed over here. We keep using the same corner. So we just keep moving half the distance to the same corner, which isn't super exciting. So you can actually use a comma here, and you can provide an additional argument to the random. And I'm going to add I to it. So when I do that, we do start to get moving towards random corners. It should look, not sure how many iterations in this is, but it should start to look somewhat similar. We've only done 100, which isn't enough. So we can go up. Ah, we did it. There it is. So we did 100,000. We're already starting to see the shape appear, which is pretty cool. You can press the D key and go to background, switch ourselves to the dark color scheme. We're a little bit closer to the visualization. And I'm just going to clean this up a little bit. If you right click on the VEX expression up there and go to expressions, edit string, you can also do Control E or Alt E shortcuts. This gives you a little bit of a more functional like code editor. I only use it for certain things, and this is one of them. If you want to indent a lot of lines at once, you can use this shortcut or this like icon at the top. And then I just hit accept. So it commits the change. It will just save you time, like instead of going through here and pressing tab a bunch of times, you can mass update lines like that. So that's pretty cool. We can increase our iteration here, go up to 1,000,000. Visually, things don't seem to be changing because we filled this in so well. If you do press the D key over the viewport, we can go back to geometry and we can reduce the point size. So each point will be drawn like at a pixel size or maybe even smaller than that. And this will just let you see even more detail. So we can go up to 10 million. And it might take a little bit of time to calculate at that quantity, but you can see we're getting really nice, sharp, crisp results now. So pretty simple, doesn't require too much code, but just with the power of loops, random numbers, and a bit of like trigonometry or vector math, we got our final result. It's pretty cool. In this next segment, we'll be cleaning up the code a little bit, kind of fleshing this out into a more polished tool or workflow, and then experimenting with some other inputs and generating some other shapes and stuff like that. So just looking at this code, you'd say it's not super well commented. So if you set this down and open the file up a month later, or you send it to someone else, that would take them a little bit of time to understand it. So we could kind of document this a little bit more clearly so it will make sense to us later on. So the first thing I'm going to do is just get rid of this. We use this to debug or just to check that our random point was getting assigned correctly. We were just seeing which one it chose. So we don't need that anymore. You can just get rid of it. You can also see it's a little slow because it has to regenerate this 1,000,000 points each time we make a change here. So I'm also going to reduce our total point number. And then another thing we can do is actually create parameters or like a UI, a user interface for some of the values that we expect or we want people to be adjusting when they look at this code. So I can completely remove that. And I'm going to make a channel reference. And then this, we'll call it iterations. And if we go to the start of where this is declaring a new channel, you can actually hint at what kind of data you expect this to be. So I'm going to add an I to it. This is indicating this is going to be an integer channel. And then if we go over here and click this kind of hotkey or little button, that profiles the code for any calls of the channel, and it creates these spare channels for us. So then we can adjust this through a parameter instead of having to change or update the code constantly. And we can even do this using like the current frame number. And then you have a interesting animation. You can do this, maybe we'll speed it up 100 times. You can kind of watch that shape being drawn in, filled in over time, which is pretty cool. Might go back maybe to bigger points. We maybe do 2. So that's pretty cool. So I might leave this 100,000. It's a pretty quick to generate, but still looks pretty cool. Then we can just go in and start to document this a little bit. So we'll say choose a random point from the input 1 geometry. Get the position of the random point. Find the direction from our current location to the target point. Move ourselves. Instead of half, I'm just going to say a portion of the total distance to the target. And then lastly here, we're just going to place, maybe in parentheses I'll say generate, because we're actually creating, maybe that's even more clear. Create a new point at the current position. If we want to move the window around just to get access to everything, it's up to you if you want to eliminate these extra lines, if you think it makes it more readable. The other way you can do that as well. So we have this parameter. We also have this number here. We might want to expose this for the user to play around with as well. This is, we can have it be a float. So we'll do CHF, and this will be our seed. So if we create that and we look closely, as we change it, we're basically choosing different outcomes or random numbers. So it doesn't, because we have so many filling everything in, it doesn't look that different, but with less points overall, this is just generating a completely new random outcome, basically. And then lastly, you can add one more parameter, and this will be our portion of the distance we're going to move. So if we change this to a channel float, and we'll just call this distance underscore scale. We'll create the parameter. If we adjust this, you can see we have some interesting controls we can make. So we can kind of tweak the code or the algorithm to get more art-directed or unexpected results for this fractal, which is really cool. So instead of just seeing a typical Sierpinski triangle or triforce, we can skew it a little bit inwards and get more interesting or unexpected outcomes. And another thing we can even do is adjust the segments that are on our input shape. So if we go up to 4, maybe 5, could play with this pentagon. And you can see as I adjust this parameter, we can even generate completely new fractals or shapes, which is really cool. This is why we wanted to expose this number here. It just gives us control over the size and distribution of the points. And that was a super important reason early on. I wanted to replace this instead of hard coding it with 3, like we were doing. You can see if we hard code that, it will always just consider the first 3 points. But if we replace that with our endpoints function, this will automatically update to adapt to the input shape. So that was a super important function to use early on. And one more thing to consider is if we want to speed this up or optimize things a little bit. Right now we're just feeding in 1 point at a time and then generating 1,000,000 points based off of that input point. So this VEX code it multi-threads, but if you just give it a single point, you don't really take complete advantage of the multi-threading because it's just running over a single point. It's just a single thread. It can't really optimize that anymore. But one thing we can do instead of running this, instead of extracting a single point and then running our code over that point, I'm going to use an add node. And this time, instead of using it to create a point like we did earlier, I'm going to use this other option that says delete geometry but keep the points. So this basically kills all the primitives, all the edges and everything, and just leaves us with the points. So now if I plug this in, we have to be a little bit more careful because it's stacking, or it's running multi-threaded, so it's going to be doing 5 times these total iterations, or doing 1,000,000 but in parallel. So if I go down now to 500,000, we're still creating a lot of points, but we're able to adjust this more quickly because we're multi-threading this code. And if we want to clean or maybe make this a little bit more expected, so we don't have to keep like compensating our total iterations based off of the input number of points, we can adapt that procedurally or automatically. So if I divide this total iteration by the endpoints, I just highlighted that and did Control-C, Control-V, but we could type it out as well. So just divide this or scale it down by the number of points in the first input. So now it will automatically adapt. So this iterations will still be valid for the total number of points that we're going to expect to generate. That's a good thing, just so it doesn't get out of control if you give it a really dense or high input mesh. And one more thing we need to be careful about is now that we're giving it multiple points, these are all sharing the same iteration counter, I, and they're all sharing the same seed. So we're not getting as good of an even distribution as we could. So we want to update our seed here, and we can add pt_num, which is going to be the input point number. So when I do that, you can see it automatically gives us a better distribution, a more even distribution. So this is without it. There's a lot of like overlapping points right now because they're sharing the same seed. So if I zoom in and look at point numbers, you can press the D key if you want to get in really close and go to view. And if we just turn on only adjust the far clip, we can type in manually a new near clipping plane, and that will allow us to zoom in really close. So there's a good amount of these numbers that are overlapping. You can see some here and some here, and then that's what's causing issues right now. And if we go back here and add the current point number to offset the seed, you can see that expands our points. So we no longer have as many, or we shouldn't have any exactly overlapping points now. Basically here, if we just look at our input geometry, these point numbers are getting used now to offset the seed. So we're multi-threading, or we're running the code in parallel now over like 5 CPU threads. If you have more threads in your processor, you can use this copy, and we're just going to duplicate points at the edges, right, the corners. So you could do like 20 threads at a time. And this, we should see a little bit of a speed up when we do it that way as well. So we're generating 4 million, but we're able to scrub this almost in real time. Okay, so I did realize I messed one thing up. We want to actually use endpoints 0 for the primary input. So now we're getting an accurate iteration scale. So that was one mistake. Sorry about that. We want to use this input to adapt our number of iterations, not the input in the second one. So we should be able to go up to 1 million. And now we're adjusting this, and it's pretty responsive, pretty quick. Sometimes this details view, it might slow down the UI a little bit as well. You might see things speed up a little bit if you hide it. So we can get some interesting fractal shapes this way. We could continue to play around with our input shape. You can see we get very interesting symmetry this way. Another thing you can do is this distance scale. You can even go higher than 1 and kind of invert your pattern and get different outcomes or different patterns this way. So maybe something around here. This is pretty cool. It's almost like a snowflake or something. And if we want to change our UI, you can click the gear, go to Edit Parameter Interface, and I'm going to change our distance scale, this slider here. We just want to change the range from 0 to 2 instead of 0 to 1. So this will just make it a little bit more clear to the users that they can go beyond 1 and still get reasonable results that way. And we could continue to try some other shapes. You maybe go up to 7. And you get even like a lace kind of pattern that's pretty cool. Good doily, something like that. And we're still working with 1 million points, but we could go up to 10 million. And once you start working with pretty high point counts, you might start thinking about like easier ways to visualize or display them or even save them out. And one thing we can do is start to convert these to images or volumes. So I'm just going to make a volume here. I can make this 2-dimensional, and we can use this XY plane. And I'll just call this density, and I'll just set the initial value to 1. So a 2-dimensional volume is almost the same thing as an image. If we middle mouse button here, you see we have a 10 by 10 by 1. So this is almost just like an image with a resolution of 10 pixels by 10 pixels. And with volumes, the actual terminology voxel means volume element, and pixel just comes from picture element. So if we think of this instead of 3-dimensional volume and just 2-dimensional picture, these can just represent the actual resolution in pixels. So we could go up maybe 512 by 512. It's like a pretty basic image size. Should be pretty easy to work with. And then if we want our fractal to fit whatever shape, we want to fit it to this kind of canvas or this volume size, we can just use the match size node, and we can scale it to uniform scale. So because we're just working in a unit range of 1 by 1, we should be good. And then we can use volume rasterized particles. And by default, the particle scale is pretty big. I'm going to make this quite small. I might have made it a little too small here. Or it's possible our resolution. Okay, so I think I see what I did. We just need to clear out that initial value. Okay, so now we're getting what I was expected. So the coverage scale is the amount of density that each particle or each point will contribute to the volume. And then particle scale is the size that it will treat it. And if we increase our resolution, we should start to see a sharper result. You might want to press the D key and go to texture and make sure you have this limit resolution. This still considers it a 3D texture because we're working with volumes. So I could go up to 2K. And now we can start to see a little bit more detail as we zoom in. So this is a pretty basic way to convert things to volumes. If we want to save this to disk as like a texture, we can even skip kind of the rendering phase of things. And we can use the Heightfields output. So Heightfields in Houdini are actually considered as 2D volumes. And this will just look for the volume that you have plugged into it. By default, it looks for these terrain layers. Usually it's called height, but we can use density in this case. So I'm just going to plug that into all the channels. We can just put this into the temporary directory for right now. If you're working on a project, you can save it wherever you'd like. And I'll just call this fractal.exr. And you can save it to disk. It might take a little bit of time. And then if we just do render, preview, just mplay load disk files, then I can go to my temporary directory. We see that we do have our image being output. And because this is in EXR, it will save all of the range, the full range of the pixel values. So you could even use this as a image map or texture map or something like that, or just use it to keep track of things that way. And one last thing we want to do is pretty cool. If we use the name SOP, we can actually rename this from density to height. And by default, nothing happens, but we can update the way that the viewport is visualizing it if we use the primitive SOP. So if we go over to volume, adjust visualization, you can change this to Heightfield. And by default, these values are super large. There's a bunch of different ways we can adjust them. One way is if you just do volume mix. You can use this for simple multiplication of volume values. So if I just scale everything down here by like 1%, then we're just adjusting the height pretty much. We could also clamp values. So if I start to actually enforce a maximum, then we're starting to like cut out specific height values and just have a maximum range. And this is really cool because you can even use all the Heightfield tools that you're used to. In our case, we need to be a little bit careful because we're working at a much smaller scale than Heightfields are usually, like really massive measurements or units. So these default parameters are usually a bit too big. But we can run all of our nice tools like blur and get a smoother height field this way. And if you want to remap or reuse these for procedural terrains or stuff like that, you can even start to play around with that stuff, which is really cool. So we just update our height field output here. We could change this now that we've renamed it to height. You can just do that. You might want to consider this auto remapping because our height values are in actual like elevation units. It's going to be a pretty dim value or like not super bright. So I'll just turn on auto remap. And we can save it again. And then if we load the disk file, it might still be saving it. Okay, so we can see we do have the blurred version now. So if we wanted to use this as a texture or whatever, we can be sure that that post-processing has been applied. So yeah, super cool. We're still working 100% procedurally. Everything should still be pretty responsive to calculate these. We could go back maybe 4 divisions, like the diamond shape. We could maybe change this, reduce the total count for a second. Play around with this stuff, get like interesting subdivision patterns this way. Can get overlapping kind of interference, interesting patterns. Maybe we'll go up to 5. You got to be worried sometimes that if you see it getting like too big or too blurry, it's just never going to resolve into anything interesting. It's almost like focusing light with a magnifying glass or something. Like if it becomes too spread out, you're never going to get an interesting pattern. But this one here seems quite interesting. So let's see, we're 4 million. Could go up to like 15 million roughly. And can explore this one as well as a height field. So maybe our blur doesn't need to be as spread out. So we'll still preserve some of the detail. And let's increase our maximum clamp value, maybe the overall value. We'll just get a little bit more shading as well. So yeah, super cool, quick, kind of optimized workflow. You can generate a lot of interesting patterns, can kind of start to combine them or mix and match them and generate your own little library of shapes and patterns, which is really cool. So far, we've just gone over a 2D workflow. So we're just flattening these out and just generating patterns. But if we want to move into the 3rd dimension or extend these to even be more interesting, we can start to do that just by replacing our input shape. So we've always worked with these flat, just a single polygon, changing the number of sides. But if we go to the platonic solids, and I'm just going to spread things out here so it gets a little less confusing. And you could hold down the Alt, select these, hold down the Alt key and drag them to make a copy. So I've just connected it to the triangle, the pyramid, and I'm going to reset our distance scale to 0.5, or what we were working with earlier. So you can see now we have extended that Sierpinski triangle into 3 dimensions and created a Sierpinski pyramid, or kind of a 3D Triforce type of thing. So that's really cool. We could even, I'm just going to duplicate my platonic input. We could go up into some of these more complex shapes, and we have the dodecahedron. I'm going to give this one a try, and maybe we want to change this distance scale, and we could start to see some interesting patterns happening. It's kind of hard to tell because we don't have any lighting being applied to these shapes, but you can start to make out at least some interesting silhouettes. I might try going the other way, up above 1, kind of inverting things or turning it inside out almost. Let's try like 1.4, 1.3. This is starting to look pretty cool. And we're just working with 15 million. We could increase that to be even higher, but I'm going to try to convert this to a volume now to visualize it a little bit better. And previously we were using the volume node because it has this 2-dimensional option, but in 3D you might want to use the VDB volume. So these are sparse volumes, which means it doesn't have to fit or fill a box. Any unused regions, it doesn't activate those voxels. So it's a little bit more optimized for 3D shapes when you're not filling in the full region or a full container. And I could continue to be calling this density. I could reduce the voxel scale. And we can keep using that rasterized particles node. So we'll plug in the base volume and the particles. Now I'm just going to press escape to cancel that. You always want to be careful with this particle scale. If you leave this at 1 unit, it's going to try to fill up a pretty big footprint for the particles. So we just want to reduce that and give it another try. So it's a little dim. We can increase the coverage scale. We're starting to see a fog, like a smoke representation of the fractal now. I'm just going to increase this and maybe get ourselves up to 45 million points. And it should start to smooth out some of these areas now. It's super not, still super hard to, it's not super clean to visualize. So we can convert our VDB volume. And if we convert this, we just leave it still as VDB, but we change it, the class from fog to SDF. SDF stands for signed distance. And when we start to do this, you'll start to see we actually get it drawn or displayed with these grids that are like little sprites that are facing the direction of the volume. So it's a little bit easier to visualize this way. And we could even convert this again. Let's go this time to polygon soup. And if we want to optimize it, you can use this adaptivity. So we'll make it a little bit more lightweight geometry. And that's pretty cool. We might want to play with this particle scale. if we reduce it, you should start to see a little bit more detail. You also might have to reduce the voxel scale. So as I do that, we increase the resolution of everything. We should start to see a little bit more detail overall. So that's pretty cool. If you want to visualize these even with even a little bit more extra fancy stuff, one thing we can do is use VDB analysis. And I'm going to use the SDF and compute the gradient of the SDF. So that will actually show you which direction the values are traveling in. And then we can use attribute from volume to sample the gradient onto the mesh that we calculated. So it's putting it into the color channel, the color attribute. If I middle mouse button here, we now have a color attribute. And this is the same thing as almost like a normal pass, or like the surface normals. If we go to perspective correction toolbar, you could look at like a single channel, and it's almost like applying lighting from that direction. We're kind of baking normals into the color channel now. And you can even do the smooth SDF. So if you want to smooth out the SDF value before you compute the gradient of it, you should start to get like a little bit more clearly or smoothly defined normals. So just for visualizing these, it's just a little bit easier to see what's going on. So if we look at particles or points, it's harder to tell. This just makes it a little bit easier. You can even copy the gradient to the actual particles themselves and bake that information into the points there. This is another thing that you can do that's a pretty cool way to visualize what's going on. So you could save any of these to disk, the SDF or the mesh or the actual particles themselves. There's all kinds of cool techniques and tricks and stuff like that you can do to render them, assigning interesting shaders or instancing these onto other geometry, assembling them into larger structures or repeating them to make even kind of like mega fractals or mega structures that have a lot of interesting and unique features. Thanks for sticking around to the end of the video. This pretty much wraps things up. If you felt like you learned something or you enjoyed it, please do subscribe, like the video, hit the bell, ring the bell, hit the gong, do all the things, retweet, share, subscribe, bookmark, repost, everything. And thanks so much for supporting me. And also, thank you so much for everyone who's supported me either on Patreon or Twitch. I have the full list of all the supporters, all the tiers here. I really appreciate their continued support, helping me continue to produce and create such high quality content. As a supporter, you also get access to bonus material like Houdini files, scene files, behind the scenes, tools, setups, workflows. Of a quick teaser of some of the things I've posted here recently. Making a flower using KinEffects. I was making a lot of different plant setups or rigs using KinEffects. I found that really good kind of like intro to rigging and the capabilities that all that stuff offers. A lot of more technical stuff using VEX. Just a lot of interesting workflows that I like to share with everyone. Render setups, if you're into Redshift, there's a lot of cool shaders and renders and stuff like that going on here as well. So yeah, if you're interested in that, it's just patreon.com/johncoons. Feel free to become a Patreon there, and you will gain access to all of this material and more, hopefully soon.